Welcome to Linear Algebra Lecture Notes section 1.7. Today we're going to understand what it means for a set of vectors to be linearly independent, and we're going to use matrices to test for linear independence. This is a very important tool that we'll keep coming back to over and over again throughout the semester. So if we have a set of vectors, and this says index, what that means is just they have a number below them. So v1, v2, up through vp in this case, in Rn. So the number of vectors doesn't necessarily have to equal the dimension of the space, but remember the number of entries in each vector equals. So these are vectors with n rows, n by 1 vectors, but there's p of them. So they're said to be linearly independent if the vector equation x1 v1 plus x2 v2 all the way up through xp vp equals 0 has only the trivial solution. So the only possible solution there is setting all the x's equal to 0. It's said to be linearly dependent if there exists some non-zero set of weights that also give us a solution. So some of these c's might be 0, but as long as at least one of those c's is not 0, then the vectors are said to be linearly dependent. So let's just try an example. So we have two vectors, and it asks if they're linearly independent or dependent. And so we have x1 times u plus x2 times v equals 0, and we're trying to solve that system of equations. That corresponds to a vector equation. And so we can write an augmented matrix and row reduce to solve. And what you'll see when you row reduce is, let's see, if we do row 2 minus 4 row 1, we get 1, 3, 0. And really, we don't need to keep that column of zeros. I'm just putting it there so you kind of see when we have a homogeneous equation, as we row reduce, we don't change anything about the right-hand side of our system. And so, this should not be negative 12. It was 6 minus 12, so I believe that's negative 6. And then we take that bottom row and divide it by negative 6. And we get 1, 3, 0, 0, 1, 0. And finally, we can do row 1 minus 3 row 2. And we're left with 1, 0, 0, 0, 1, 0. And if you think about what these equations mean, that first equation says x1 plus 0x2 equals 0. So x1 equals 0. And that bottom equation says that x2 equals 0. And so that means that the only possible values that you could attach to x1 and x2 are 0. So these vectors are linearly independent. And we usually use an Li. If we had a free variable, so if one of the columns was a free variable, then we'd have multiple solutions, and that's when our vectors are linearly dependent. Let's look at what happens if we have a single vector. So that's saying we have x1 times this thing here equals the 0 vector. Well, you can write that as a system of equations, and what that looks like is negative x1 equals 0, 3x1 equals 0, and x1 equals 0. And in fact, this tells us that x1 has to be 0, and so again, this vector is linearly independent. So if we have just one vector, it's going to have to be linearly independent. Okay. So now for our quiz, we have two vectors, and again, you're going to want to test, is there a non-trivial solution for the equation x1u plus x2v equals 0? And so my hint is you make an augmented matrix, you get it to reduce echelon form. Really, you could actually answer this question with echelon form, because what you care about is there a free variable? If yes, then it's linearly dependent. If no free variable, then it's linearly independent. Okay. So in general, what can you say about two vectors if they're linearly dependent? So you should have seen in the quiz that these two vectors were linearly dependent and they lie along the same line. If you graph them, what you'd end up having is 1, 4, 1, and then a multiple of that, 2, 8, 2 in that case. So in general, if you just have two vectors, you have x1 times u plus x2 times v equals 0. If they're linearly dependent, then that means you have some c1 and some c2 that make this equal to 0, which one of c1 and c2, let's say one of c1, c2 is non-zero. And let's just say c1 is non-zero. Well, that means we can divide by it. So if we divide by c1, we get u plus c2 over c1 times v equals 0. And we can actually just subtract that second term from both sides, so we get u equals negative c2 over c1 times v. And so what we have then is one of these vectors is a multiple of the other. And so, in other words, they lie along the same line. Okay, so now we have another quiz. This is the same exact idea. You want to determine whether these three vectors instead of two are linearly dependent or linearly independent. And you may row reduce if you'd like. So you can row reduce and look for a free variable. And remember, if there is a free variable, then it's dependent. Then the vectors are dependent. If there's not a free variable, then they're linearly independent. But sometimes there's shortcuts. And one thing you can notice here, if you think of these as a system of equations, you have negative 8x1 plus 3x2 minus x3 equals 0. And then that next line says 2x2 plus 3x3 equals 0. And the last line says x3 equals 0. So you notice right off the bat that x3 equals 0, and see if you can go back through and figure anything, based on that, figure anything else out about x2 and x1, and that will help you with your quiz. Okay, so now we have a couple of more general questions. So let's say we have a set UVP that's linearly dependent. And so first of all, let's go ahead and write down, before we do anything else, that means there exists C1, C2, and C3 that are not all 0, such that C1 times U plus C2 times V plus C3, oops, sorry about that, times P equals 0. And so now the question is, can we then turn that into a linearly independent set? So right now we have a dependent set. Could we turn that into an independent set by adding a W? And well, the answer is no, because anytime you add that W into your set, you can make a dependence. So this is called a linear dependence. You can create one by using that dependence from U, V, and P and just tacking a 0 in front of W. Because remember, our coefficients need to not all be 0, but we already know that one of C1, C2, or C3 is non-zero. So this is, again, a linear dependence. So we know that are set. Once a set becomes linearly dependent, we can't add anything in to make it independent. We will learn later about strategic ways to delete things to make them make the set independent. So you can delete to make something independent. And now our quiz asks us the other way around. So if you start with a linearly independent set, can you toss in another vector and turn it into a linearly dependent set? Okay, so our last two questions are again talking a little bit abstractly. So given an example of 4 linearly independent vectors in R3, or explain why it's not possible. Well, let's think about what happens if you have one linearly independent vector. You get a line, right? You just get that line. When you have two linearly independent vectors, they point in different directions. And so geometrically, they create a plane, which is something that's 2D. A line is 1D. And similarly, once you have 3, you're going to have to get outside that plane, or else you're in the span of those two vectors. And so you get something 3-dimensional. So if you have 4 linearly independent vectors, then you need to be in a 4-dimensional space. But this problem tells us that we're in R3, which is 3-dimensional, so it's not possible to have 4-dimensional object in a 3-dimensional space. Just like you can't fit a plane onto a number line. And now finally, this last question asks us to write an equation to prove that the set 0, v1 through vp is linearly dependent. And we said it's in Rn, it doesn't really matter what n that is. The point is, because we have 0 in here, no matter what v1 through vp are, it's always going to be linearly dependent, and here's why. You can take the 0 vector and multiply it by anything you want. I'll choose 17, why not? And then you can take 0 times all the other vectors in your set. And since that very first vector was the 0 vector, even though it was multiplied by 17, it stays 0, and so the whole thing just becomes 0. And so this is, again, a linear dependence. A linear dependence is the relationship that shows a set of vectors is linearly dependent. You will always be able to find one. There might be more than one. In this case, we could do 15, we could do 5, we could do any number we want in front of that 0, or there might be a dependence even among the v1 through vp. So linear dependence is a relationship that shows that a set of vectors are linearly dependent.